Okay, the next issue is how we are going to denote this electric field. We on like now first let's review how we represented vectors. Now vectors have a magnitude and direction, so we use an arrow. The length of the arrow gives the magnitude, and the direction is given by the length of the line gave the magnitude, and the direction is given by an arrow. Now it's not possible to use a similar idea here, because let's say here is a positive charge and we want to denote the electric field. So it's a electric field. This region is a region of space where a positive stationary charge is going to experience a force, right? Now if this positive stationary charge is placed here, let's say that it will experience 10 Newton force. I'm just saying. So I'm representing 10 Newton using 1 centimeter line. Approximately this is 1 centimeter. Now let's say that this stationary charge is placed somewhere here and it would experience 5 Newton. So I would draw a line which is half of this 0.5 centimeter. That's fine. But the issue is, in this entire region, this positive charge or this charge is going to experience a force, not only just here and here. So what's going to happen, how we are going to denote it? If you put the charge here, it would experience a force, and yes, it would be a bit less than 10 Newton because it's a bit further away from this point. But if you try to draw that line, part of the length of the line and part of the initial line will coincide, and you will have a line like this, which makes no sense. If the lines are connected, then you won't be able to distinguish what is the length of the vector denoted for this position and what is the length of the vector denoted for this position. And that's going to happen everywhere, right? So we need to come up with some novel creative idea of how we are going to represent it. So pause the video and think for a couple of minutes. If you are the first person in planet Earth who was facing this situation, what kind of a solution you would come up with? For example, shall we use the thickness of the line? That means in a place where the field is strong, we draw a thick line, and a place where the field is weak, we draw a thin line. So pause the video and think for a couple of seconds. Okay? If you have thought of your own way of representing, let me tell you what is the standard conventional way of representing. We draw lines indicating the direction in which a positive charge would move. So let's take that here there is a positive charge. I'm not talking about this positive charge. The one we are going to place here, that should be a positive charge when you are defining the direction of the field. Then obviously this will repel and that charge is going to move outward. So this is how we denote the direction. Now in terms of the strength of the field, we use the gaps between the field lines to denote the electric field strength. Now if you look here, in this region the field lines are closer together, right? There are about 4 lines passing through this much area. But if you draw the same size of area here, if you put the same size of area here, only 2 lines will pass through it. That means the field lines are far apart here. We use the gap between the field lines to denote the strength of the field. That means this field strength is very large here because the lines are closer, and the field strength is weak here because the lines are far apart. Okay? This is the case for a positive charge. So if you draw for a positive charge which is spherical, okay, a spherical positive charge, then this is how it's going to look like. I am putting the direction outward by imagining another positive charge placed in that region and in which direction that positive charge is going to experience a force. Now if this was a negative charge, then if you put a positive charge, that positive charge would move towards, so the direction would be opposite to this. Here it's towards the charge. But as far as the strength is concerned, yes, strength is higher closer to the field. Strength is higher closer to the charge, and the strength reduces because the gaps between the lines increases as we go away from the charge. Okay? So the field lines have the property of being drawn considering a positive charge. So in other words, the lines of force start on a positive charge and end on a negative charge. That means if you have both positive and negative, then if you put a small positive charge here, that charge is going to be repelled from this charge and going to be attracted by this charge. So it will move in this direction. It will experience a force in this direction, the resultant force. And the field will be denoted like this, and here it will be denoted like this. You need to be careful that, look here, the field is closer, the lines are closer here compared to this place. The lines are closer compared to this one. That means the field is stronger here compared to here. Okay, so the first property of an electric field line is the lines of force start on a positive charge and end on a negative charge, because we draw it in considering a positive charge. So a positive charge is going to repel and a negative charge is going to attract. So the lines of force start on a positive charge and end on a negative charge. So the second property is the lines. Forget about the second property for the moment, then look at the third one. The strength of the electric field is indicated by the closeness of the lines. Okay, the closer they are, the stronger the field. Now the second property, the lines of force are smooth curves which never touch or cross. Now why they should not touch or cross? Because these lines indicate the direction in which the object is eventually, the positive charge is going to eventually move. So if a positive charge is here and the line is indicating in this direction, then it means it is going to move in that direction. If there are two field lines which are crossing, let's say there is another field line which is crossing, that means that the field is indicating that a particular charge is going to move in two directions at the same time. That's not possible. An object can only move in one direction at one time. Okay, so that's why the field lines cannot touch or cross. So the field lines have the following properties, the above three properties, which you must take into consideration. Then the field lines for different patterns are shown: the spherical charge, then a positive and a negative charge, then a positive spherical charge which is earthed. And this is a very important one. Here if you look, in the middle the lines are parallel and the gaps between them are equal. The gap indicates the field strength, so equal gap means equal field strength. Sorry, we're going to look at that in detail in the next video, but the thing is the strength is being same because the gap is equal. Okay, now if you look at this, particularly this positive charge here, now within this positive charge there is no field line, which means there is no force going to be experienced by a charge if it is placed inside this region, but outside only there are field lines. But the beauty is all these appear to be coming from the center of the positive sphere, right? Inside there is no field lines, but the field lines outside appear to come from the center, which means that you can treat a very small sphere as an approximation for point charge. Now, point charge means a very small charge, a very small charge. We need that in defining electric field strength, which we will need which we will see in a couple of minutes. But we can't have just a point positive charge. But what we can have is a very small sphere, and that small sphere can act as an approximation to a small point charge because the field lines appear to come from the center. But be careful, there are no field lines inside the sphere. It is just like the virtual image thing. The virtual image is formed in a place where it appears, the light rays appear to come from, or like the center of gravity scenario, the point where the weight of an object can be considered or is appearing to act. Okay.